Okay, fine. So today we're going to see model number three in our fluent problem. So the problem goes something like this: a water flowing through a converging nozzle of diameter zero point 0.5 meter to 0.25 with length of 3. So he has given the velocity and temperature 0.01 and temperature 25 degrees respectively, and the density of water, dynamic viscosity, and boundary condition he has given. The first boundary condition is to the wall is maintaining constant temperature of 100 degree. The wall is maintaining constant heat flux 5000 watt per meter square. Consider inlet temperature as 100 and heat coefficient as 500 watt per meter square degree Kelvin. So we need to calculate inlet velocity, outlet velocity, mass flow rate, grid independent test, check for flux balance, plot temperature, pressure, velocity, contour, etc. So compare the calculated value with simulated result, velocity and temperature. Okay, fine. So basically, this is our problem. So the reason why we taken when we see this problem, it is a nozzle. It's a nozzle problem. So basically, it has an axis. Okay, it has a center axis. So what we're going to do is we're going to take only the top off. We're not considering the entire part. Instead of that, we are going to take only top off. Why? Because it is an axis symmetrical problem. It's an axis symmetrical model, which means whatever it is in top, the result will be same at bottom also. So we are considering only the one half of the problem. This type of problem it is called as axis symmetrical problem. It is a symmetrical problem basically. Okay. So these are all the calculations. Okay, calculation part we are not going to touch. We are going to touch only the software part, and we are just going to compare whether the result is valid or what. So this is our ANSYS Fluent workbench. So I'm going to select. These are the various solver, as you know. Whatever you see on the left side, these are the various solver. Like for our case, we are going to take fluid flow fluent, and I'm going to drag and drop here. So let me go step by step. Okay, so this is your fluent. So basically fluent has how many steps you need to carry out. You need to carry out 6 different steps. Can you see? These are the 6 different steps. So the first step is it is a fluid flow problem, fluent. The second is you need to prepare a geometry. Third one is mesh. Fourth one is setup, which means after meshing, we're going to give the boundary condition, that is setup. Once the setup is done, you need to solve, which means the matrix will run and it will give you the solution. Then you will get the final result. These are the various steps you're going to follow. So here I'm going to teach one more thing, grid independent test. That is a new, like I have found a new method that I am going to teach here. So first we're going to start with the geometry, the very first step. So just right click, second option. When you right click, you will get a second option, new geometric modeling. I have just clicked. Yeah, this is a dialog box comes. This is a design modeler we're going to use, or modeling workbench. Okay, basically it has 3 axes. I'm going to use the first one, XY plane. Right click and type look at. Right click and type look at. So your 2D plane comes something like this. Now what I'm going to do is I'm going to open my model. I'm going to check what is the dimension I need to give. So basically, it's an nozzle which has 2 diameters. It's a tapered, like it's a tapered nozzle. So the inlet, it is a converging nozzle. Basically, the diameter keeps on reducing. The inlet diameter is zero point 0.5 meter. exit is 0.25 meter. So when we take this as axisymmetric model, we are going to divide this into half. I think you are aware of it. So first thing what you're going to do is I'm going to click on unit and I make sure whether it is in meter and it is in degree centigrade. I mean degree. Uh, Basically it's a thing which used to measure the angle degree. So this is a meter. So I'm going to draw the sketch. So I have selected XY plane. I'm going to use sketch. I'm going to open line. Before line, I'm going to constrain this because I want to build a relationship between this like plane. So I'm going to use constraint. I'm going to click on coincident. Then I'm going to draw a line. So I'm going to start from here and I'm going to just roughly draw how the nozzle looks. Since it is an axisymmetric model, just I'm going to draw roughly the off section of the nozzle, as you can see here. Just roughly I'm going to draw. Once this is done, I'm going to give dimensions. I'm going to choose. There are multiple ways of giving the dimension. Like I'm going to use only horizontal and vertical. Now I'm going to click vertical. So I want this dimension, a vertical dimension. So I'm going to click two horizontal lines and I'm going to extract it so that I'll get vertical dimension. Again, I'll show you. Clicking on vertical, I'm going to click on horizontal lines and I'm just dragging it out so that I get vertical dimension. Similarly, if I want to draw the horizontal line, means I should click on vertical lines and drag it down. I'll get an horizontal line. This is the way you need to give the dimensions. Once, if you're done with this, see at the left bottom, you can see dimensions. I have given three dimensions: h3, v1, and v2. So what is v1? This dimension, we know it is 0.25 because it is a off section of the nozzle, axisymmetric model. Okay, v2 0.125 and the length of the nozzle is 3 meters. Once it is done, you can view the model. So this is the nozzle, axisymmetric nozzle. Till here, any doubt? Do you have any doubt? Am I audible? Do you have any doubt?
No.
Okay. Once this is done, I'm going to generate it. See, until and unless if I don't give this generate, what happens means like our model or the Fluent will not understand whether you have saved your problem or not. Once the sketch is done, you need to just click on generate. Don't forget this. Once it is generated, you can see here the sketch is done. Now what I'm going to do is once the sketch is done, I'm going to click on sketch. Here, I'm going to click on concept, surface from sketch. I'm going to click that. And I'm going to give apply. I clicked on sketch, I clicked on concept, I clicked on sketch from like surfaces from sketch. Once it is done, it shows something like blue color. I'm going to generate. Once I have generated, the lines become planes. The lines becomes planes. This is the most important part. Once this is done, I'm going to assign what is my inlet, what is my outlet, what is my edges? All the edges I'm going to give the names. So what I'm going to do is, can you see this option? Selection filter edge. I'm going to click this. I'm going to give the names by clicking each edge. Select it, right click it, name selection, named selection. Click that, change the name. What is this? Basically, what you see is the inlet of the nozzle. So I'm going to give inlet, and enter. See, it has come as inlet. Generate. I got a tick mark, which means the Fluent understood this edge. This edge, it is my inlet. Now I'm going to give the exit. Clicked it, right clicked it, going to write outlet. Generate. My outlet is done. This is my wall and this is my axis. Okay, so I'm going to click this, right click, name section. I'm going to give that as wall. Similarly, I'm going to click this. There is nothing but axis. So basically what I have done, I have created a geometry, I have created a plane, and I given the name for the edges. That's all. This is geometrical work. If you have any doubt, you can ask.
No doubts.
So I'm going to close the model. See, my geometry part is done. Now I am going to open machine part. It takes time. Okay, you got the model. I'm going to click this one. Can you see this coordinate at the right corner? So I'm going to click the Z so that I am going to get the required plane. So XY plane I'm going to get, because XY plane is normal to the Z. Now I'm going to give meshing. So how to give meshes? Go to mesh, go to mesh, right click, insert, sizing. Okay, select this one. I'm going to select this plane, inlet. When I click that, I'll get something like this, which means it is apply symbol. When I apply it, you'll get something like this. So here what I'm going to do is I'm going to use number of division. For instance, let me use 50. I'm going to divide the inlet into 50 divisions, which means I'm going to chop it into 50 parts. And I'm going to click this one as P. Very important. And I'm going to give generate. See, the meshing is done at the inlet. Again, I'm going to use mesh, sizing, outlet. You can give separately or you can give at one particular stretch also, it doesn't matter, but I'm going to give separately. Same thing, the top wall, since the length is very long, I'm going to give as 150, or you can even increase to 200 also, doesn't matter. See, all the four corners is been properly meshed, but in the face, when you see the face, it is not regular, it's totally irregular. So what I'm going to do is, I'm going to mesh the face also by using face meshing. Just select and rivet and generate. Once it is done, you can see the beautiful meshing is done. See, it is well organized, beautifully it has been meshed. This is all about meshing. So you need to know how much, like how much it is meshed. Just click on mesh. The last option you have statistics. In this you have nodes and elements. Okay, we want how much elements it is. Just click on this, you'll get P and close mesh. See, once you close mesh also, it doesn't update. See, there is a symbol. It shows it is not updated. Now what I'm going to do is right click. I'm going to update.
We are doing third model, right?
Yes, third model.
And what is that parameter set? Even I will get that sometimes.
Okay, I'll tell you what is that parameter set. See, when you're meshing it, I'll open mesh. I'll reopen the mesh and show you what is that parameter set. See, actually, what is parameter set means, it is it's like a memory. Okay, it's like a memory. It will save certain values. For example, I'm going to mesh and just see. There is a small, uh, tiny word P. Can you see here P? If I deselect, you can deselect. If I click, it will select. Okay, that P is nothing but the Fluent will save that value of P, that how much division you have been divided. Okay, how many number of division you have divided the inlet mesh, it understands. So it's basically, it saves the small quantity of value for grid independent test. You can use the grid independent test like once the model is done. I will tell you what is that, but for time's sake, you remember this. I have saved for all the things. See, if I click mesh, I have also saved for statistics. For elements also, I have saved this. I want this thing to extract that particular value back. So this is very important parametric set. There is a small tiny box. If you click that, it shows you P. For my problem, I don't want how many nodes I like. I want how many elements I want. Element is a main important factor. Okay, for extracting the value for grid independence test, I'm basically use this. If you have any doubt, you can ask me. Okay, fine. Can I move forward?
Yes.
Okay, geometry is done, mesh is done. So I'm going to start with setup. See, basically, what type of problem it is? It's a 2D problem. We are not yet discussed what is 3D. We have discussed till 2D problem. So I'm going to use double precision. What is double precision means? See, you're going to get very accurate result when you click on double precision. So that's why we use this double precision, and I'm going to start it. Can you see? Can you see my CD like converging nozzle? So basically, what we have done is we have just prepared a model. Now we are going to give the boundary condition for that nozzle, like that particular nozzle. What should be the inlet? What should be the outlet? What should be the temperature? What should be the heat flux, mass flux? All those things we're going to calculate it. So basically, in general, there is various step for assigning boundary condition and calculation. In that first one, you have general. Don't change anything. Don't change anything. Okay, because it is a pressure based, absolute, steady. In 2D space, what type of problem we are discussing is axis symmetry. Only this thing you should change. Suppose if I using absolutely a convection based problem means I'm going to use this density based and gravity. Absolutely convection. Part of convection, absolutely convection means I'm going to change this too. Or else all the things should be default.
In convection case, we are going to give.
Density based and transient gravity, these things will change. Absolutely convection, I like I'm not going to deal with any other heat transfer. Only convection problem we're going to use this. Partially convection, no problem. Absolutely convection means I'm going to use this three: density based, transient, and gravity. Fine. So now what I'm going to do is I'm going to go for model. In model, I'm going to open. So you have various type. Before that, I want to check what type of problem it is, whether it is laminar or turbulent. Like based on our calculation, we found this problem is a turbulent problem. It's a turbulent problem, and he has given in problem statement. He has given there is a heat flux and heat transfer also taking place. So what we basically going to do is we are going to on energy, because there is a heat transfer taking place. Energy we are going to on, and in viscous we are going to use k epsilon, because in viscid there is no viscosity. There is a laminar, rest others everything is a turbulent. In that we are going to use k epsilon model of turbulent. We're not going to use k omega or other kind of thing. Only we're going to use k epsilon in our problem. This is a basic turbulent model. Rest everything should be a default. You should not change and never change. It depends based on problem. But for our problem, all the other things are default. K epsilon, give OK. So it is done. So basically in model we have on energy and as well as in viscous we are on as like turbulent K epsilon turbulent model we are on. Next, going like selecting the material of the nozzle and as well as what type of fluid is just flowing inside the nozzle. So material, I'm going to open with material. What type of material we are going to use as per the problem statement? Water flows. Okay, and specifically he has not mentioned what type of nozzle material we're going to use. So whatever default we're going to retain it same. So the flowing fluid is water. So we are just opening this. Let me show once again. We are opening material, fluid. In fluid, I'm going to click. It opens something like this. I'm going to click fluid database. In fluid database, I'm going to click on water and I'm going to copy it. So I can even change the values also, but for my current problem, it's not required. Whatever default value it is there, I'm going to save it. I'm just going to copy that. Okay. I'm just going to copy and close. Sorry, by mistake I've like taken two different values. I'm going to delete that one. Water liquid I'm going to keep. Only water liquid. H2O in liquid form. So solid I'm going to keep default as aluminum only. I'm not going to change anything. So next I'm going to cell zone condition. In cell zone condition, what is the surface? My fluid is subjected to water surface and I'm going to give apply. No other thing is changing here. Next I'm going to give the boundary condition. This access inlet like surface outlet wall. So basically let me see the problem and accordingly let me give the boundary condition. So first I'm going to give the velocity as a boundary condition with inlet temperature as 25 degrees centigrade with no slip condition. So the constant wall temperature is 100 degree centigrade. So let me click inlet.
One second, you open cell zone condition.
Cell zone condition, surface body. I'm just changing to water. It was here. I'm just changed to water. That's all.
Okay, okay.
So boundary condition, inlet automatically takes as inlet velocity inlet. What is the velocity? 0.001. Okay, there's a small mistake. It is 0.01, not 001, 0.01. And temperature is 298. At 298 degree Kelvin, my inlet velocity is 0.01. That's what it means. Apply. At outlet, what is the condition given at outlet? Pressure is zero, which means this is a static pressure. It should be zero. It is zero. I'm not going to change anything. At wall, it shows wall temperature. I'm going to take wall temperature, just temperature, the second option. At wall temperature, it is 373 and material is aluminium. I'm going to save it. Close it. So this boundary condition is default. Now I'm going to methods. All this method doesn't change. I'm going to monitor residual. I'm going to change the residual to optimum value 1 exponential minus 16. So we'll get very good, it converts very fast. So I'm going to sell, sorry, I'm going to installation, hybrid installation. I'm going to install the problem. It is installed. It is installed. Now I'm going to run the calculation. So
Hello.
I'm going to give 250 as
Hello.
the iteration. Yeah,
I think in initialization we should go for hybrid standard initialization.
hybrid.
Be- because their temperature, all temperature should change,
Why standard
So,
installation?
one sec, like, come down full. Their temperature should change now. 369. That should be like, wait, not that one.
Should we
That
change
should
here?
be like, 298 it should be.
298. Why 298?
Inlet temperature we have to give.
Okay.
There, you go up. 1 second. Full up. Yeah. There. Yeah, there you select inlet like that. Inlet.
Okay.
That's all.
I didn't know. Fine.
Okay.
Okay, fine. Okay, thank you.
Maybe hybrid also will work.
Yeah, hybrid it takes automatically.
Uh-huh.
Okay. Like actually, it's good to learn this also
Okay.
because latest version hybrid takes automatically.
Okay.
So the problem is converging. It is converged. So once it is converged, the one very important thing that our problem is said to be correct or
Show
not.
the graph.
You're going
Show
to
the
that's what
graph.
before checking the graph. This is a residual.
This one.
And show the residual separately. See picture preview. Okay. Okay. So whether my problem is right or not, how can I check? Means I should go for fluxes. Like in results, report discrete phase like fluxes. Let me click fluxes. There, let me check inlet and outlet and compute it. See, when I compute it, it's showing that my inlet and outlet mass flow rate remains the same, which means whatever the value I have done, it is correct. So just carefully observe this. Mass flow rate at inlet, I am saving this. I am typing as mass inlet. Similarly, outlet, I am going to save mass outlet. Okay. Now total heat flux. So I'm going to check the wall, inlet, outlet. I'm going to compute it. So I'm getting some this value I'm getting. So let me check what is the analytical solution for it. I think we don't have analytical solution. We have not solved it. But anyhow,
ಇವನ್ ಐ ಕೊಡ್ತಾ ಸರ್.
let me keep this wall heat flux. Flux temperature boundary condition. Wall heat flux temperature boundary condition. I'm just saving it for my future reference. So now I'm going to the surface integral. I want some values to be taken. I'm going to use facet average. Here I'm going to check my inlet velocity. I'm to take inlet velocity. Inlet velocity. I'm going to take minimum exit velocity, maximum put velocity. So I'm going to take maximum pressure at inlet because outlet is zero. So temperature, minimum temperature, temperature and maximum temperature. Let
Wrong.
yeah, just a minute. I'm going to say mass flow rate also at inlet and outlet. Mass flow. Fine. Yeah, you can ask the question now.
You can explain once again what is this?
See, surface integral means because this works in constant volume process. Because in surface there is a control volume gets in and gets out. So at surface, what are the changes happening? We are going to basically deal with. So at inlet, what happens? Outlet, what happens? Phase shift average means at inlet, maximum is like these are the three conditions. At surface phase, what is the average temperature, average minimum temperature, and maximum temperature, pressure, and velocity, minimum, average, minimum, and max. So accordingly, going to select and save that. Okay, I'll tell what is that and how it works. Once you know how it works, you will get an idea. Okay. Meanwhile, just understand what is this. Okay, fine. So once I done with this, I'm going to close this. Before that, I'm going to save this. One while saving it asks two options. Use setting change for correct calculation only. For future calculation, I'm going to give future calculation and give OK.
So we are giving that surface integral for next step. Huh?
Yes.
Okay.
So I'm going to take as model 3. Model 3. I'm going to give model 3 C nozzle. Now what I'm going to do is I have created geometry. I have done the mesh. I have given the boundary condition. Now I'm going to solve grid independent test. So how I'm going to do grid independent test means I'm going to click on this parametric set. See, it will open something like this. See various parameters. What and all I saved, everything it has come. Minimum temperature, maximum temperature, all those things. What I did just before in surface integral. Now I'm going to increase the mesh here only. I'm going to go 55, 60, 70, 65, 70. Now I am going to give update. So what happens means basically the fluent will run and it will increase the number of mesh. It will increase the number of mesh. It takes long time, very long time. We'll see how fast it does. It takes long time for computation. Did you understand this?
Yes.
See what's happening. My grid size is keeps on increasing. My element is keeps on increasing. So it takes long time to solve. We'll see. See, there is a change in the output maximum velocity. The maximum velocity we are expert is 0.044. Let me check with analytical whether we are going in the right path or what. 0.04. We are going in right path. See, temperature. Look at the temperature. So, what is the maximum temperature? We need to get need to solve from our results. How much I got? Okay, some value I got. I'll remove this and I'll put the new one. One set of values. I'll put the new one. Okay, grid independent test is done. So yes, so let me take these values, how much ever I want. Stop it. So mass inlet and mass exit remain the same. So it doesn't matter. There is no significant change as we see. Carefully copying all those things. See, the negative indicates that it should balance. The mass inlet and output, it should be negative. I'm going to remove this negative so that we just need a magnitude that is sufficient. So let me update in simulation also. Last value, the same doesn't matter. So I'm going to check the velocity. So inlet velocity is zero point 0.1, doesn't change. So exit velocity maximum changes slightly because finer the mesh, we are getting finer values. There is a reduction of the errors. So maximum pressure. Okay, I can make out properly this is a converging nozzle because at inlet velocity of nozzle is low, pressure is high. So when the velocity at the exit it is maximum, the pressure is zero. It's almost zero. Only static pressure, like static pressure is zero. So temperature. on increasing. This is doesn't change. This is our independent test. So let me take the last value. So this is your minimum grid so that we can get like very nice because we can go for more number of grid also. For our current problem, this is sufficient. I'm taking 12,000 elements, reasonable value. Okay. So let me extract graph now. I'm going to take contours, velocity contour. So velocity contour. This is my velocity contour. I'm going to save this. I'm going to save safety. Changing as velocity temperature contour. So temperature contour. Temperature contour. I want to extract pressure contour. So till now it is okay for you, right?
Yes.
Now we need to take plots. This is very important. Plots. I'm going to open XY plot. I'm going to establish a relation between the nozzle. Like what happens when it is approaching at inlet. At different points, I'm going to plot a graph. So basically, contours will give the entire surface of the nozzle how it is affecting. But whereas our XY plot determines at particular point of the nozzle how it is subjected to various pressure, temperature, and velocity. So basically, I now what I'm going to do is these are the parameters. I just want inlet and outlet with respect to inlet and outlet. So what I'm going to do is I'm going to measure those quantities in terms of mm, y direction instead of x. Okay, or is like vertically I'm going to move. So what I'm going to do is I'm going to make x as 0, y as 1. Horizontal I'm moving something. I'm going to move something like this. It's not like this. I'm going to move. If I have a scale, or is like vertically I'm going to move. So I'm just going to click inlet and outlet. I'm going to see the nature of graph. Look at that graph. At inlet, what is the pressure? At outlet, what is the pressure? As you know, at outlet it is zero. It is zero. At inlet, it is going to max. I'm going to save this. I'm going to type save this as y pressure. So similarly, I'm going to find the velocity at inlet and outlet. See what basically happens is at inlet it enters as a constant velocity. At outlet it is gradually it's trying to raise. See the velocity is increasing, and when it is goes out of the nozzle, like it slowly it tries to drop. Let me save this. So I am going to take one more graph, that is my temperature 0. I'm going to take as 1 0. I'm going to establish a relation between the wall with respect to axis. Wall with respect to the axis. Or I can even establish with respect to wall with respect to the interior surface or surface body, whatever it is. But now I'm going to establish with respect to the wall. Static temperature, if I give total temperature, I think this graph is so this is how you need to extract this graph.